I don't think so. All right. So now we're in the midst of this warm-up, and what we said we want to get slope-intercept form is y equals form, or y equals mx plus b. We did that by, let's say, moving the 4x over and dividing everything by -3. So we've got a negative y-intercept there at -2 is my y-intercept. And then it's got a slope of 4/3. So up 4 and to the right 3. So 1, 2, 3, 4, 1, 2, 3. And there we go. Oh, that's a crummy line. No. But one of the things that we're going to be doing today, a lot of, is graphing lines, and actually like graphing 2 lines and seeing where they cross. And so obviously I'm just kind of using this warm-up to help me practice graphing a little bit, also to talk about manipulating a formula. Now with number 3, let's see here, D, what do I do on number 3 where it says solve for x given that y equals 3?
Subtract 26.
I asked D, I didn't ask whoever that was over there. Well, it says given that y equals 3. So what happens if y equals 3 is I can substitute it in. So I got 7x minus 3 times 3 is 9. And then it becomes a matter of a simple 2-stepper. Freddie, hit me up. What are my 2 steps? Good. So we get x equals 5. Beautiful. Finley, hand up. What you got?
Number 2, why is the 4/3 also 5?
All right, good question. When we quote, quote, move that 4x over, so if I had -3y equals -4x, that's what happens. And then another way of looking at it would be to say these 2 guys switch sides. And when you change sides, my friend Coach Gray would say you change signs. And so like moving that 3x over becomes positive, dividing both sides by +3. Bada bing, bada boom. All right, fabulous. Yeah. So the old switcheroo, you guys will see, BJ, I think you just asked it. You'll see a lot like in situations that come up sometimes in trigonometry. So I might have like the sine theta equals 2/3, right? That's a relationship that you guys will learn when you study trigonometry. Okay, and so you might end up having something like, well, I don't know the fraction, but I know everything but the denominator. And what I'll tell my students is you can pull the old switcheroo. In other words, these 2 guys would swap spots as well. It's just inverse operations, but you're just sort of taking a shortcut approach, right? Because what would I do if I wanted to get x by itself? I would have to times both sides by x, and then I would have to divide both sides by sine. In essence, what they've done, and I wish this pen would work better, is that they have switched sides. They have switched sides. I think I might have to break down and go to IT and request a new stylus. We'll see. But yeah, that's the old switcheroo. Nicholas.
So a quick question. What is trigonometry like actually?
It's relationship. You study the relationship between sides and angles in various shapes, mostly triangles, but different shapes as well. So like, for example, not to let any cats out of any bags, but like, let's say I have a right triangle right here, and this is an angle, then the, quote, sine of that angle would be the ratio of the opposite side compared to what we call the hypotenuse. And have you all used words like opposite, adjacent, hypotenuse before? Okay, stuff like that. That's basic right triangle trig, which is a lot of what y'all will study 2nd semester with me. All right, so that being said, fabulous questions. Thank you, guys. We're going to look now at, quote, solving systems, something you should have done in Algebra 1, okay? So this is meant, this sort of first week's lesson here is meant to jog your memory and get everybody on the same page here. So solving a system means I've got more than one equation that I'm considering at once. And there are 5 ways I'm going to teach you to solve these systems. All right, let's see if we can, in our notes, we can maybe name a few of these techniques that you've learned over the past. Mitch?
Graphing.
Very good. Graphing. Christian? Substitution. Very good. Stephen? Elimination. Excellent. you very likely have not learned the other two. Alex? I guess maybe that's kind of like a ish way of doing that thing. There's one that's called Kramer's rule that we'll learn about this year, and there's one that involves matrices. And I don't think anybody has really done a lot with matrix operations. But in Algebra 2 Trig, we will talk about Kramer's rule and determinants, and then we'll talk about matrices. And what's really helpful?
Boxes of numbers.
Yeah. Like a matrix is an array of numbers. It's got rows and columns, and we'll study that. I think I've got that lined up maybe in Unit 2. So, and then of course, I'll teach you how to use a calculator to solve these lickety-split, okay? But first things first, we got to understand, what does it mean for it to be a solution? You're looking for all the points that are on both or all three or however many lines you've got. You're looking for the points of intersection. Good, Mario. The points of intersection. So like for this one right here, it says, is the point 5, 2 a solution to this system? What would y'all say? Excuse me, 5, negative 2.
Yes.
Yeah, 5, negative 2 is the point of intersection. In other words, it gives a true statement in both equations. All right, and that's real plain and simple. You're just looking for the point where they intersect, and we would say, yes, it is a solution. Okay, I use the analogy, if we were walking down the street, let's say Phil and I go for a walk. We're walking down Walnut Grove Road, just in the middle of the doggone road, Phil. All right, and then we get down there to White Station, and we are sitting in the intersection, middle of the intersection. Cars are dodging us left and right, and let's say Phil makes a proclamation. He says, I am on Walnut Grove Road. Is that a true statement that Phil just uttered? Yeah. What if I said, I am on White Station Road? Would that be true?
Yes.
Yes, because we are at the intersection. We are on both roads. And in fact, you guys have heard that word intersection before in the context of a what kind of diagram? A Venn diagram. Good. Let's see, Nash, could you describe the intersection of groups A and B here? Very good. It's the overlap. So you've learned about Venn diagram intersections. The word intersection could be used in that context. Yes? By the way, if I take time to write it on the screen, you should probably write it in your notes. We've seen the word, because we'll use this in probability this year. Okay, Venn diagrams, we'll use them quite a bit. All right, you've seen intersections with regards to inequalities as well, right? So you might have seen something like, well, X is, give me a good preposition here. A preposition, please. Any grammarians?
Between.
Ah, who said between? There we go, Mr. Cocker. So yeah, X is between 2 and 5. Another way of writing that would be to say, hey, X is greater than 2 and X is less than or equal to 5. And when we graph that on a number line, guess what we're looking for? We're looking for the overlapped region. You know what I'm saying? So this word intersection is a powerful word in math. Whether you're on a Cartesian plane over here and you're looking for where do those lines cross, you're in a Venn diagram, you're looking for where do those, like, let's say this is a group of students that I teach algebra, and this is a group of students that play on the Christian Brothers basketball team, right? Then the intersection would be the group of kids that do what? They do both. And I've got how many? 2 in this class? 3? Oh, that's right. Cochran and Bill and Mr. Brown. And who else? Ah, sweet. So I got lots of basketballers in here. Very nice. But you get the idea of what the intersection means then. And so what would the sort of the other word that we use besides intersection? Excellent. Air 5. It's the union of 2 sets. All right, now I asked Cochran, let me ask, let's see if Mr. Denegri could tell me, we'll change colors here, what would the union of 2 sets look like? What do you think, Andrew?
Like on a number one?
No, I'm drawing a Venn diagram. Okay, so would this be considered part of the union class? No. Would this? Yes. Would this? Yes. Would this? Excellent. So we don't use the word and, we use the word or. And so this would be visually what the union of two sets looks like. Number line inequality business. If I said x is less than 0 or x is greater than 1, there you go. Right? And you're not looking for an intersection. You're just looking for, and not both, you're just looking for at least one. If at least one is covered. That would be like if I said, today I'm going to teach math, or I'm going to go play golf with my son. Okay? As long as I do at least one of those, I've told the truth. Okay? What if I said, today I'm going to teach math, and I'm going to cook breakfast for the math department? I got to do both. What if I said, today I'm going to teach math, or I'm going to cook breakfast for the math department? I could do one, the other, or both. So the word or is a little bit less
There's a situation where it's like one is like on the other side of the other and it goes that way and that way makes all real numbers.
Yeah. To where like there, even though there's an overlap, and that's where it really depends on what the word is that you're using. All right. So fabulous. We talked a good amount about the word intersection, a union, all these good words we're coming up with. Now I want to look at example 2 and 3 with me, and I want you to tell me, how would you figure out, oh, I'm going to hit you up, Aiden. Roberts, you get dibs on this one. How would you figure out whether or not 6-1 is a solution to that system? What do you think? Plug in what for what? Look at Finley helping out like a big boy.
Yeah, Finley.
All right, so you would plug in 6 for X and 1 for Y. Where?
In the equation. Both equations.
Good. We've got to make sure it's we plug in, we get a true statement in both. Okay? And so you could do that. Now, I believe that you guys are good at plugging things in. I do. And so at this point, I'm going to show you a little calculator technique. Okay? Show you a little calculator technique. I mentioned that I will try to sprinkle in a little bit of like how-to on these calculators. Here's your first how-to. Here's your first tip. Here's your first little strategy. So if you got one of these calculators, you can get it out, and I'll show you what I'm gonna do here. Pardon me? Who made it roll away? Who should we blame? Phil? Phil Connors? Nobody? Somebody said it? Yes, bonus point for that man.
Who said that?
Groundhog
Is it Groundhog Day?
Was that the guy who comes up to him on the street?
No, that's the,
Yes,
That is a great movie.
yeah, I forgot.
Groundhog Day is a day in the year, I thought, not a movie.
It's a movie.
Finley, I'm disappointed that you don't realize Groundhog Day occurs in February. It's like February 2nd. Michael did just earn a bonus point, by the way. If you impress me in class, Alex remembers, you know what I'm saying? So like you can earn a little bonus point. So like, let's say on our first quiz, Michael earns a 4 out of 5. That point at the end of the quarter, I'll add that in, and it will bump his score up a little bit. So kudos. Groundhog Day, if you hadn't seen it, funny movie, but we got to get on with our stuff. Do what? Oh, it's a funny movie. All right, so here's what we're going to do. I'm going to teach you about what this STO button does. STO. All right, so it's a store option. Okay, and so what I'm going to do is I'm going to store the numbers 6 and 1 for X and Y. Or technically, I'm going to do A and B just so I don't mess anything up. Sometimes if you store something for X, that can kind of mess things up. So here we go. I'm going to hit, what was X supposed to be? 6. I'm going to hit 6, store, and then alpha A, enter. Okay? So now, every time that I type the letter A, guess what that's going to come up with? It's going to come up with the number 6. Can y'all see that all right up at the top?
Yeah.
Okay. And then I'm going to similarly, what are we storing for y? 1. All right, so I'll hit 1, store, and then we'll just use b so I don't mess anything up. X and y, I typically shy away from using X and Y. It doesn't really mess anything up, but I think it's a good habit to get it into. So now what I can do is I could say if I've got some complicated funktastic equation, I can type that in, and what is 2x minus y equal? It equals 11. So that's a true statement. That's a thumbs up. Similarly, I could say x plus 4y, and that equals 10, and that's again a thumbs up. Now you might be saying, Coach, that's stupid. I could do that way faster on paper or in my head, and I 100% agree. I'm just using this as an illustration of a calculator technique of how you can store a value in your calculator. Okay? Because when you get into some more complicated stuff, it might be helpful to be able to store a value for a particular letter. All right, so number one, storing a value does not affect the functionality of your calculator at all, assuming you don't store it for X. And really, when you store it for X, it doesn't affect the functionality either. But if you really were OCD and you wanted to clear it out, be very careful, cuidado. If you hit second and the plus sign, it takes you to this memory management and deletion section. And what you could do is you could go through and you could, I forget which one it's at. I would not delete any of those. You could go, oh, there we go. There's A and B, and you could hit DEL and DEL. And there you go. And so now the default, I think, is 0. So now it's back to default. But to be honest with you, I wouldn't mess with that if I were you. Mario?
They should restore value like you restore A to 1, they try and store it again.
Yep. And you know, where this might come in handy, do y'all study chemistry this year? Have you learned the number 6.022 times 10 to the negative 23rd yet?
No.
Avogadro's number? Y'all had something about that? So like, imagine you've got a number you're supposed to memorize or you're supposed to remember, and you like do a lot of calculations with that number. It could be real helpful, instead of typing 6.022 times 10 to the negative 23rd over and over and over again, just store it. Just store that value. So that's a fun little calculator trick for you. Again, with regards to our example, it's much faster just to plug and chug, and you guys can plug and chug in your head. Also, Desmos would be helpful as far as graphing that out. You could plot both of those and see where they cross, and they would cross at 6.1. How about negative 3, 4? Did y'all get to check that example yet? Negative 3, 4. Let's see if we can do this in our head. Negative 3 times 2? Negative 6, perfect. 4 times negative 3?
Negative 12.
Negative 6, negative 12? Ooh, I like that. All right, let's try it again with the second one. Negative 3 goes for X, so negative 3. 4 goes in for Y, so 4 times 2? 8. 8 and negative 3? 9. As my son would say, womp womp. Okay, that did not work out. And so is it a solution? It is not. Tell me what you do know about the point negative 3, 4, graphically speaking. What's something that you do know?
It's not on the intersection.
I like how Phil raised his hand.
It's not on the intersection.
That's true.
It's in the top right, top left.
What quadrant do we call that? Quadrant 2. Okay, so it's in quadrant 2. Phil?
This is on the line at the top of the
That's exactly what I was going for. It is on this line, but not that line. So imagine Phil and I are out there and we're walking on Walnut Grove and we're not to the intersection, but I say, I'm on Walnut Grove. Yeah, that's true. And Phil says, I'm on White Station. And we're like, womp womp, you're not. Okay? So it's got to be, in order to be the solution, it's got to be in both. That's what we're looking for. Now, you guys will find yourselves in one of 3 scenarios. One of 3 scenarios. Either the 2 lines we were studying, they cross, they don't cross, or they're actually the same line and they have infinitely many points of contact. So we call these systems independent, dependent, and inconsistent. Okay? Both of these are technically consistent because you can find a solution. The dependent one has infinitely many, so it's more in line with that. What is something, Michael, What's something that you know about parallel lines?
They will never cross.
Besides the fact they never cross. Like something that you might know about their equations, perhaps?
Oh.
Let's go back to Kenneth. Kenneth?
Same slope.
They have the same slope. All right, but they have different, Henry, what do they have that's different about them?
Y-axis.
Y-intercepts. Very good. So parallel lines have same slope, different y-intercepts. All right, Mitchell. What about a situation in this like dependent scenario? Tell me about those two pieces of information.
They have the same y-intercept and the same slope.
They got same slope and same y-intercept. They are in fact the same line. The reason I'm making this point is because on ye old Delta Math, I've got you guys a nice little assignment up there. And one of the question types says, determine the number of solutions in the system. And so what you want to be able to do is you want to be able to ascertain whether or not it's same slope, same y-intercept, same slope, different y-intercept, or just different slopes altogether. All right, so let's check this. Do these guys have the same slope?
No.
Try again.
Yes.
Yes, they do. Do you know how to calculate the slope of a line in standard form? It's the opposite of A over B. Write that down. The opposite of A over B. That's the slope of a line in standard form, so that you don't have to spend time solving for y, putting in y equals 4. It's the opposite of A over B.
Is it the opposite of A over B or the opposite of A over B?
Either one. You can put the negative in front of the fraction or on top, just not with both. Mario?
You're right. You said the opposite of A over B is what?
How you would, first, yes, just give me a second. The slope of a line that's in standard form will be the opposite of A divided by B. So we've got -4/5. Now over here, we've got 4 over -5. Again, same slope. So we know it's not, which one could we eliminate? We can get rid of the one solution because they have the same slope. So it's either going to be no solution or infinitely many. All right, and the way that we would determine that is we would check to see, is this number going to match up when these two numbers match up? So in other words, if I divided everything by a negative, I would get 4x plus 5y equals -9. Same exact equation. So the same exact equation means what? Infinitely many solutions, right? Yes, sir.
They cross over the same point.
In different what?
Like,
So two lines, if they cross, have to be coplanar. But if they don't cross, they don't necessarily have to be coplanar. They could be skew. But everything we talk about in this context is the two lines are on the same plane. They're both coplanar. Good question. That is spoken like a true geometer. Mr. Perry would be proud. Let me go back to the notes, but you kind of see, look, there's their explanation. They actually use elimination, which we'll talk about in just a moment, to check. They kind of do a linear combo of the left and of the right, and they get a true statement. But again, we'll check in a sec. Here's what we're dealing with. Those three scenarios. Okay? And then when you start looking at nonlinear systems, right, what do I mean by a nonlinear system?
Parabola.
Yeah, you might have a quadratic equation whose graph is a parabola. Later on this year, we'll talk about conic sections. You might have, we might come across one sometime like where you've got an ellipse. A dadgum pen would work. There we go. And a parabola. And how many points of intersection would that nonlinear system have? 4. Yeah, it'd have 4 points of intersection. And so your job is going to be to figure out what kind of scenario you're dealing with, no matter what the system is that you're dealing with, or that you're analyzing. Bless you. Everybody comfy with this screen? We ready to slide on? Okay. Am I right that this is something y'all learned in Algebra 1? I feel comfortable with this somewhat. Remember, we got a lot of different guys with a lot of different backgrounds as far as Algebra 1 goes, so we want to make sure we're all on the same page solving these systems. Graphing, I think, is the easiest way to solve a system. when you are doing it on a calculator. Being good at figuring out where two lines cross on the calculator, real basic skill. Finley, what's up? Gotcha. Gotcha. Were you guys good?
Yeah.
All right, perfect. So here's a couple of examples to gander, take a look at. We'll minimize ribbon. Yeah, there we go. Okay, perfect. A couple of ones to take a look at, and I want you to try the first one by hand. BJ, you try the first one by hand, and then I want us to try the second one using the graphing calculator. So if you got a graphing calculator, we'll try doing the second one on there.
When the slope is negative,
Down and to the right. So negative slope, positive slope. And if it were a quadratic function, positive leading coefficient, negative leading coefficient. Field goal or swole patrol. Alex, I'm glad you paid attention. All right, so y'all are graphing that first example, the example that's at the top. You're graphing it by hand, and let me encourage you: make your tick marks equally spaced apart, make them equidistant, and that way it'll be easier for your lines will be straight, your graph will be easier to read. And yeah, graphing paper makes things super easy. Now, do we have to be like completely anal retentive and getting out like a straight edge and a ruler and making sure? No, we just got to ballpark it, and we'll try to figure it out. While y'all are doing that, I'm going to punch in the second one on the graphing calculator.
Get it ready for the calculator to put pi on one side.
Mm-hmm. Yes, sir. And by the way, you might notice the fraction syntax, like how to type a fraction in. So like if I go ahead and type my numerator, like my numerator is -1, all right, and then I hit alpha or this little green button, alpha x, then that automatically auto-populates that numerator that I've already typed in. And then it just allows me to type in the denominator, and then you got to get out of the fraction by scrolling to the right. So -1/2 x minus 1. Question or comment? All right, so you'll hit alpha, that green button right there, and then X, and that kind of auto-populates. Real nice little shortcut. There's another shortcut menu. If you hit alpha y equals, you'll see there's a sort of a shortcut menu for not just fractions but mixed numbers as well. And then there's some conversions between fraction, mixed number, or fraction, and what do you think D stands for? Decimal. So like if you hit alpha F1, that green F1, that takes you to a shortcut menu for fractions, which can be quite helpful.
How do you click enter? How do you do the enter?
Oh, that's what I'm going to show you next. Great question. All right, so if you hit graph, isn't that nice and pretty? We got our two lines graphed out. One's in red and one's in blue. That's why we like color edition. And Mr. Buckle.
Yeah, how do I zoom out?
Beautiful. Can I go full screen on this? You guys ready for me to do that? Y'all written down the examples? And also, can you kind of tell those of you that don't have a calculator yet, you want to get one soon? Okay, because we'll be using these a lot. So zoom is in the top center. If you hit zoom 6, that 6th option is standardizing the window 10 left, 10 right, 10 up, 10 down. Zoom 6 is your friend. Anytime you're graphing, hit zoom 6, and that will sort of centralize your picture. And then what you'll notice is the red one was my Y2, and the blue one was my Y1. And you kind of pay attention to that. But almost said Zach, to Mitch's question, if you hit second and then trace, second, trace, it takes you to your calculations menu, and you can hit the fifth option, which is intersect, and then just check this, just hit enter, 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 and it will tell you where they cross. Hey, what's up?
Can I see Mitch?
Yeah, absolutely. He's right
Oh, nice. Come here, just real quick.
All right, so again, real quick and real helpful way of finding the solution to a system, especially if they if they intersect at integers, at nice, neat numbers. Mitch.
Calculator says invalid dimension.
All right, did you hit Zoom 6 yet? Hit Zoom 6. Hit enter to quit, and then hit Zoom 6. Just the number 6. All right, so go back to your right, hit enter, and go back to your white. And then you got plot highlighted, so scroll up, and then hit enter to de-highlight plot, and then you should be ready. Second trace, fifth option, number 5, or you can scroll down here. I've got lots of questions. Let me come kind of swing through and help out. No, I think it requires this one's totally fine. Your plot you got your
Something.
it's like
Hey, who's the standard?
that's okay. It's just so like if you wanted to do, let's say -1, so that -1 divide by -2, and then yeah, Christian, this is a scientific calculator. It's not a graphic calculator. So a lot of what we'll do this year will be on a graphic calculator. Yeah, where's you in that? Okay, let me show everybody. Down in 5. Hey, real good question came up. All right, there's a big fat hairy difference between this button right here and this button right here. This is a minus sign. Do not use it in the context of like typing in a fraction as negative. This is the negative sign. So when you go to your y equals, it will give you an error message if you used the minus sign in front of your fraction. Now you use the minus sign when you're subtracting, that's fine, but use the negative sign when you were negating. That make sense?
Who did that?
No, Mitchell didn't do that. Aren't you nosy?
I would get, I guess.
Michael and Blake asked that good question. Michael and Blake get kudos for that question.
That's a good question.
Mitch, or Mitchell, excuse
How
me.
do you find like the intersect? Mine's was always like small that.
So if you'll hit second, calculate, and then 5, enter. That'll do it for so I think Mitchell's got a good point. In summary, what we could do is we could say that I go to y equals, and then once I've got my functions typed in there, I'm going to hit second, trace, and then enter. Those shortcuts, man, you can get quick at it. Okay? So once you get it loaded into y equals, hit second, trace, 5. I left 5 out, sorry. Second, trace, 5, enter. And man, you're talking about kids that can get some AP scores and some ACT scores up, or those kids that know the shortcuts, know the short keystrokes, and can plug and chug on those calculators. So we partnered with, this is gonna, I hope impress you. We partner with a school up in Tipton County that has been teaching, it's like some friends of Dr. Whitmer's, that have been teaching like an ACT prep class, and they on average have gotten their kids to increase their ACT scores by 3 points by doing like little workshop stuff like what you and I are talking about in this context. And so like, now of course this is just the context of math, but like being purposeful about preparing for tests like that, you will see advantages. Now you guys are like the cream of the crop. Y'all are all the smarties, and so y'all are getting your scores up there because that's big time scholarship dollars. Where like there's a big fat difference between a 29 and a 30, let's say on the ACT, and you get a lot more money with the 30 than you do with the 29, for instance. So we want to learn these little shortcuts. Want to learn these little hacks. Oh, here's my screenshots. Perfect. So you would type them in. This was from an older calculator, okay? And then you would hit second, trace, enter, 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 and or 5, enter, 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 and then it gets you squared up. Okay. Now, part of the reason why you guys are learning how to solve systems is so that you can apply said system solving ability in terms of a word problem or like an application. Okay. So what I'm going to leave you with today, I think I've got about 10 minutes, 12 minutes. What I'm going to leave you with today is this word problem, and the hard part isn't solving the system, it is writing the system. Okay? So let's see if we can remember something from Algebra 1. However many unknowns there are tells you how many what you need to write.
Variables.
Okay, variables you need to write. So however many variables or unknowns there are, let's say in this example there are 2 unknowns. That means I need to be able to come up with 2 what?
Equations.
I need to be able to come up with 2 equations. What if there were 3 unknowns?
3 equations.
You'd have to write 3 equations. And 4 and 4 and 5 and 5 and so on and so forth. In Algebra 1, y'all dealt with 2x2 systems and maybe some 3x3 systems. Depends on how quickly you were going through it that year and how much time you had in your curriculum for your teacher. All right. In Algebra 2 Trig, in this class, we're going to learn to solve 3x3 and 4x4 and 5x5 systems. 5 equations, 5 variables. Okay. What do we have at our disposal that makes that really easy? Calculators. Nash.
Is there like a website I could go on since I don't have my calculator yet that I could do the calculator graphs and on my laptop?
I think it costs you money. You know what I mean? Like, if you went to TI, Texas Instruments, and you wanted to download the, what do they call this program? SmartView?
There's software for it?
Yeah. I think they give you the software when you buy the device. But if you wanted it like earlier, if you just wanted it on your computer, I think they'd probably charge you for it.
I found like a website or 2 years ago.
Mhm.
Or it wasn't a website, but like,
Had an emulator on it?
yeah, you can download the thing, the software that these run on. You can run it on your computer.
Awesome. Y'all feel free to farm that out to each other. Like Nash asked a question and Mitchell has some experience, so y'all just chat each other up. I used to use a TI-83 flash debugger was what it was called, but hardly anybody uses an 83 anymore, and this calculator is the new one that we use. So anywho, I digress. You could probably find it if you searched on the internet. I just don't know where. Anybody able to help me come up with an equation? You've been reading this for a minute or so. Mario, what's one equation?
0.8x plus 3.5.
All right, and can you explain, so 0.8x plus 3.5y, is that what you said? 3.5 equals y. Gotcha. All right, can you, wait a minute. Why are we using x and y?
The flat rate is 2.5, so that'd be like the higher intercept, and the closest and 0.80 is 34 miles per hour is slow.
All right. So I know what you mean because I'm a math teacher. Let's say we had a guest in here that wasn't a math teacher, and they read the problem, and they see the instructions are talking like C and M. Can you kind of help me reconcile, like what's the variables that they're asking you to express?
C would be y.
So C is our dependent variable. Y is usually the dependent variable. Y depends upon X. So in this case, C, or the cost, depends upon M. What does M stand for? The miles. And that's independent. Henry gets into the cab. Henry can go as far as he wants to. So that's the independent variable. Except, Nicholas, did you catch the little curveball through here?
It's for every quarter mile.
Bingo. All right. So 80 cents for every quarter mile, and yet M is going to stand for every mile. So should we do maybe, what's 80 times 4? So 3.2 M plus 3.5 equals C. All right, now that's one equation, but it's got how many variables in it? It's got 2 variables. BJ, you and Finley paying attention, I hope? Yes, sir. Beautiful, thank you. All right, so if we got one equation in terms of 2 variables, that's a dependent scenario. There's infinitely many ways to solve this equation because it's got 2 variables in it. I need another equation to lock it down. Who could come up with my other equation? Mr. Alexander.
So it would be 3.2 plus 3.5 times however many miles. I guess.
All right, so
Well, no, it would be 3.2 times however many miles plus 3.5.
all right, and do we know however many miles?
6.25.
So is M equal to 6.25? Is that what we're saying? I didn't actually read the problem yet. It costs a flat rate. I got that. Amtrak to Wrigley plus every quarter mile traveled. So that's good. 6.25 is the number of miles from the station to the field. How much money does he owe the driver? Okay. So this is boring. This is actually an easy one. What technique would we employ? Substitution. Okay. So let me take it from boring and make it more interesting. What if I wanted to solve this by graphing? Let's see here. Michael, what kind of line would this be? This is our independent, in other words, like X. This is like X equals a number. What kind of line is X equals a number? Pass it over to somebody.
Flat.
Okay, all lines are usually flat.
Vertical.
Oh, very good, vertical line. Excellent. All lines are straight, but this one's vertical. Fabulous. All right, so like if I were going to graph this out, then this system would be where we would have a diagonal line. Its y-intercept is 3.5, and it's going up, and then we've got a vertical line right there, and we would be looking for the what? Point of intersection. Now, you guys told me it'd be easy, just plug and chug. So at this point, have we found our cost when M equals 6.25? What does C equal? How much? So $23.50 would be how we would answer the question there. It says write a linear equation for the cost of the ride. We've done that in the first case right there. Okay, Freddie. Absolutely. Yeah, I didn't go to the trouble of showing that step, but you're totally right. And by the way, what's it a good habit to use when you're plugging something in? Very good, Mario. Parentheses. So when I plug that in, as Freddie tells me, I'm going to use parentheses where that M was, and we'll plug in 6.25 in there. Okay? BJ, is that hand up?
No.
Okay. Gotcha. Nash? Okay, so it was 80 cents for a quarter mile. So we did 0.8 for every quarter mile, and in 1 mile, there's 4 quarter miles. So that's why if M stands for every mile, we did 0.8 times 4, and that's where we got our 3.2. Does that help? Let's do it this way. Okay? How many quarter miles are there in 6.25? 25. Very good. So there's 25 quarter miles. So we would say, oh, well, I'm going to do 25 quarter miles, and it was 80 cents for every quarter mile. 0.8 times 25. You could do it that way too. You get the same value. Makes more sense? Perfect. Good question. By the way, you guys get more out of this class when y'all ask questions, so kudos to those of you that have done so today. Let me leave you with your homework assignment. It's on Delta Math, as I mentioned, and it's got 4 problem types. We've talked about 2 of them today, right? Solve this system graphically speaking. It actually wants you to graph it out and see where they cross. That's cake. And then I'm going to lean on you to do a little bit independent work for me here. Elimination and substitution. Let's see what you remember as far as how to solve those kinds of systems. They give you these 2, and you can solve them out. And what I'll do, remind me on Friday to show you this application. It's called Polynomial Simultaneous Equation Solver 2. It's a mouthful, but if you look at it, you can go through, and you guys that are tech savvy on the calculators, 2 equations, 2 unknowns, and then it allows you to type those in, and it will tell you what the solution is. I find that a bit burdensome. I just graph it out and see where they cross. Alex.
I got a question on the,
Problem set.
yeah.
All right, let me shut down the recorder now.